Dear students, here we are going to discuss about the electric field in material space. First of all, we know that there are different types of material. Then we know that the materials are metal, semiconductor and insulator. It is also said to be non-metal. Whenever we consider the conductivity in the different materials, if suppose conductivity is greater than 1, then we say that this is the metal. If the conductivity of the material it is less than 1, we can say that it is at low conductivity, therefore the material is insulator. Here the conductivity of the material, this is the important part. When we consider the conductivity, unit of the conductivity is Siemens per meter. The material whose conductivity lies somewhere between metal and insulator called as semiconductor. The conductivity of the metal, it is given as 10 to the power 7 Siemens per meter. The conductivity of the semiconductor, the range is from 10 to the power 0 to 10 to the power 4 Siemens per meter. If the conductivity, then we can say that the material is semiconductor. And if conductivity it is less than 10 to the power minus 4 Siemens per meter, for the material insulator. We know that here when we see the electric field in the material space, if we consider electric field in any material, electric field is there, then we can say that there are two quantities which are always there. Electric voltage, that is also called potential difference, and current are the two fundamental quantities in any electrical devices, in any electrical engineering. Then electric current is generally, we can say that flow of the electrons. Here we considered electric current is generally caused by the motion of electric charge. The current, it is measured in ampere. If suppose in a small amount of area, in a given area, the electric charge passing through it per unit time, it is said to be current. Okay, definition of the current is, in a given specified area, the passing of the electric charge per unit time, it is said to be current. If suppose current is represented as I, Q is representation for charge and T is representation for time, then here I, which is equal to dq by dt. What is the meaning of it? The charges passing through the specified area per unit time. It is called current. Then current measured in ampere, charge measured, unit of the charge is coulomb, and time in second. Therefore 1 ampere, which is equal to 1 coulomb, divided by 1 second. When we consider the concept of here current density represented using the capital J. If the current density J, it is given as the current delta I passing through a surface area delta S, it is said to be current density. What is mean by this? Delta I is the small amount of current passing through a surface which is considered small surface of the material. Through the small surface delta S, the current passing through it delta I, known as current density. If J is the representation of the current density, it is given as the current delta I flows through a surface area delta S, which is equal to Jn, which is equal to delta I divided by delta S. That is said to be current density. In another way, how to define the current in terms of current density? The delta is defined, delta I is given as delta I, which is equal to Jn. Jn is the current density into delta S. Say equation second. Here assume that the current density is perpendicular to the surface, then and then only we consider this type of equation second. If it is not perpendicular, then perpendicular means current density is perpendicular to the surface means if suppose small amount of surface area, when we consider the flow of the charge to that area, how it is the direction of the charge. With if suppose perpendicular, then we can say that delta I, which is equal to Jn into delta S. If it is not normal to the surface, then current is defined as current with delta I, which is equal to J dot delta S. That is, say equation third. Thus the total current flowing through a surface S is given as the total current. Delta I is the small amount of current passing through small amount of here small area, surface area delta S. If we consider the total current flowing through a surface, S is the large area if suppose, and delta S is the small portion of that surface. The I, which is given as I, which is equal to integration over a surface J bar dot ds bar, equation 4. Depending on how I is produced, there are different kinds of current densities. Okay, that is convection current density, conduction current density, and displacement current density. Equation 4 shows that the current I through S is the flux of the current density J. Then what is mean by convection current? Convection current is different from conduction current because here it does not satisfy Ohm's law, and it occurs when the current flowing through the insulating medium such as liquid, gas or vacuum. We can consider as whenever there is current flowing through an insulating material such as liquid, gas or a vacuum, then we can say that this is the type of here convection current. Then how to consider that convection current? By using one of the filament. Consider this is one of the filament. Here it has small amount of surface area delta S, small amount of here delta L for the surface area delta S. You can say delta L is the displacement and rho v is the charge density, and u, small u, is said to be velocity. This is one of the filament. Here surface area ds we consider as surface area, dl is the displacement of the charge. Here u is the velocity of the charge and rho v is the density of the charge. Then how to consider the different parameters for the convection current? See here, consider a filament. If there is a flow of charge of density rho v at velocity in the y direction, the current through the filament is given as here delta I, which is equal to dq by delta q by delta t. We know that this is the small amount of current passing through that area, specified area delta S, and it is given as delta q divided by delta t. Delta q is the charge passing through a area per unit time. It is said to be current. We know that. Delta q is given as delta q, which is equal to rho v into delta S into delta L. Therefore, we know that delta S and delta L represented as a volume. Therefore, in the next step, delta I, which is equal to rho v delta S into u suffix y. What is mean by u suffix y? In the y direction. Okay. In the y direction, the charges flows. Therefore, this is the very important part when we consider the uy. Uy, it is considered as velocity and it is the rate of change of displacement, means delta L divided by delta t. It is uv, uy. Therefore, the current density at the given point is current through a unit normal area at that point. Okay. This is by considering the filament. If we consider here current density in the y direction, if suppose, then current density is given as we know already, J is the representation, delta I divided by delta S, current passing through the surface area, it is said to be Jy. Say equation 6, put the value of delta I there, delta I, which is equal to rho v. Say equation 5, if suppose see the equation 5, delta I, which is equal to rho v delta S uy. Put here in the equation in the j quantity, j which is equal to delta I divided by delta S, put the equation, Therefore delta is cancelled. Therefore delta y it becomes rho v into u y. In general, this is in the y direction, but in general we can consider as j, which is equal to rho v into u. This is considered as the given expression number 7, equation number 7. It is represented as here convection current density in ampere per square meter. Okay. When current is convection, then this is given as rho v. It is said to be density of the charge multiplied by the direction of the velocity j bar, which is equal to rho v u bar. It is said to be here convection current density. Now what about the conduction? Conduction current requires a conductor like as copper or aluminium, any metal. A conductor is characterized by large amount of free electrons that provide conduction current due to an impressed electric field. When the electric field E is applied, the force on the electron E with charge minus E is, if suppose there is one metal, for the metal positive charges are applied and negative charges are given, then the motion of the, if suppose the electron flows from negative to positive, while current direction is opposite to that electron, and the force which is considered in that, it is given as, this is the force for one electron only, F, which is equal to minus C into electric field. So equation second, that is force which is equal to minus C into electric field. The equation number 8 shows the force acting on one electron only due to the electric field. Here it is electron which is available, it is not in free space. It will not accelerate under the influence of electric field. It suffers the constant collision with the atomic lattice. If suppose there are large number of electrons which are moving, then we considered as what is the drift current. How to define? Then here, if the electron with mass m is moving in an electric field capital E with an drift velocity u, then we can consider as here Newton's law. See here, the electron with mass m is moving in an electric field E with an average drift velocity u, then we can consider here Newton's law. Newton's law is the rate of change of momentum is equal to force. This is said to be Newton's law. The Newton law is applied here. The average charge in momentum of free electron must match the applied force. Therefore, here small m is the mass of electron. We know that small u is the average velocity of the charge, and tau is the time between two here collisions. When we consider here the equation m into u divided by 2, which is equal to minus e into capital E. Consider here velocity, which is equal to, velocity is u, therefore velocity is represented as u, which is equal to minus e tau divided by m into e. Say equation 9. Here e is constant, tau is constant, and m is mass of electron is constant. Therefore, we can say that the drift velocity of the electrons is directly proportional to applied field. This is the very important. This shows, equation 9 shows here drift velocity of the electrons is directly proportional to applied electric field. This is for one electron only. If suppose there are n number of electrons per unit volume, the electric charge density then given as electric charge density is given by using rho v, which is equal to minus n into E. We know that, say this is equation number 10. We know that the current density is given as current density, which is equal to rho v into u. Therefore, here rho v, we know that rho v is equal to minus n into E. For the n number of electrons, put the value of rho v, put the value of u from equation number 9, then it gives n into E square tau divided by m into E. Consider the conductivity. Conductivity is given as using the sigma. Sigma, which is equal to n into E square into tau divided by m. If suppose this is the conductivity, then J in terms of conductivity, current density in terms of conductivity is given as J, which is equal to sigma into electric field. Equation number 11. In this way, we considered as the convection current, if suppose it is in the dielectric material like as liquid, gas or vacuum, then how convection current, the current and current densities are defined. and also for the conduction current, the different here current and current densities, how it is defined. Okay. Okay, thank you so much.